Okay, thank you very much, Niharika. Right. Yeah. So, my name is Mitradip Bhattacharjee, and I am from Electrical Engineering and Computer Science from Indian Institute of Science Education and Research, Bhopal. So, today I'll be talking regarding printed graphene FET for pH sensing. Uh, that particular FET was developed not for pH sensing. We are also targeting biomedical applications. So, as we progress in this presentation, I'll discuss. But before I start the presentation, I'd like to give you one brief introduction of IISER Bhopal. So IISER Bhopal is one of the IISERs among 8 IISERs currently in India. And IISER Bhopal is unique in the sense natural science is common more or less in all the IISERs. But in IISER Bhopal, we have engineering sciences and economic sciences, both the departments. Within engineering sciences, we have 3 different departments: electrical engineering and computer science, data science and engineering, and then chemical engineering. I belong to electrical engineering and computer science department. So with this brief introduction, I'll also give you the introduction of my research group. So we work in the field of sensors and systems, flexible and wearable devices for various applications, mostly for healthcare, then biomedical and bioelectronic devices, and IoT and wireless systems. So in this particular talk, I'll focus on sensors and system domain, where I'll discuss electrolyte gated field effect transistor. And then I will also discuss its pH and biosensing capabilities. Because this particular field effect transistor is not an traditional field effect transistor, so you won't get an conventional characteristics. So I call it field effect sensing. And then if time permits, I'll quickly browse through what else we do in our group. So why pH sensing? So the pH sensing is very much important as far as the environment monitoring is concerned. So just by sensing the pH of water, you can check the potability of water, whether this water is drinkable or not. In agriculture, in aquaculture, pH sensing is very important because all these aquatic animals, they survive in a particular pH. If this pH fluctuates, then many of the aquatic animals actually can't survive in the aquatic body. Then for smart farming, soil quality monitoring, even for air quality monitoring also, we do pH sensing. So I'm not going much in detail with why pH sensing is needed. So I just gave a brief idea. So I'll quickly go to the topic today, which is graphene field effect transistor. So to start with, I have given the structure of FET. So in conventional FET structure, you have source, drain, and gate. And in this conventional structure, you also have a 4th electrode, which is known as bulk electrode, which is not shown here. But mostly these devices are made on semiconductors, silicon-based devices usually. And if you look at the graphene field effect transistor, which geometry-wise looks similar, you have source, drain, and then you have gate electrode. But in the place of channel, you have graphene present. And then this graphene channel is separated from this gate electrode using a dielectric, which is also same for a conventional FET structure. But there is a catch when you make it an electrolyte gated field effect transistor. So you remove this dielectric layer and replace it with an electrolyte. Now, the moment you replace the gate dielectric with an electrolyte, the physics or mechanism associated with this sensing or field effect transistor remains, it doesn't remain the same as you can find in conventional FET structure, but it changes. I'll discuss. But what remains the same is your drain current will be a function of number of charge carriers present in the channel, the gate voltage that you apply, and the drain voltage. Drain voltage meaning the voltage between drain and source. Gate voltage meaning that voltage between gate and source. Usually we ground the source. Now, why graphene? So graphene, everybody knows that it's a very multifunctional material. But in this case, we choose graphene because it has high surface modification ability. So you can immobilize a lot of water molecules biomolecules on top of graphene. And then it offers higher sensitivity because electrical property of graphene also allows the sensor to be highly sensitive. Apart from that, it also offers low noise and it's biocompatible. Now, if you look at the graphene band structure, you'll see that in case of graphene, the both conduction band and valence band meets at a point. We call it direct point or direct point. Also, this point known as charge neutrality point. And then if you apply a VGS value, that is gate voltage, which is greater than 0, then the Fermi function, that is the Fermi level, which is at the direct point, will shift upwards. If VGS is less than 0, then Fermi level will move downwards towards the valence band, given that this energy is electron energy. And then you get a transfer function, something like this, which is an U-shaped transfer function, where the right-hand side denotes the N branch, P branch, depending on the majority carriers present. Because it's an ambipolar in nature, so for VGS greater than 0, you will find electrons are majority. For less than 0, holes are majority. And vice versa, whatever it is. But in this case, unlike conventional FET, you don't get a switch off condition. So even at 0 VGS, you may find that the charge still gets transferred from source to drain. So there is nothing called switch off condition for this transistor. But wherever this ID current is low, we call it VCNP. CNP stands for charge neutrality point. Now, if you dope graphene, say you are doping graphene with P-type dopant, if it's an P-doped graphene, your CNP shifts rightwards. If it is N-doped graphene, your CNP shifts leftwards. So based on that, based on the doping of that particular channel, you'll see there is a change in the CNP position. Now, because it's an electrolyte gated field effect transistor, the majority of the phenomena depends on the electrical double layer that is formed near the graphene channel. Now, if you look at only this part of this FET, you can see that based on the surface charge of graphene, it will form an electrical double layer. This particular layer is known as Stern layer. And then beyond that, it forms a diffuse layer where the charge concentration decays. And then slowly it goes to the bulk solution where you'll see the screening effect. That is more or less charge neutral, this region is. Now, in case of biomolecule detection, one has to be very careful that the reaction takes place within this region. Specifically, at least, it's better if the reaction happens in the Stern layer, but it at least have to happen in the diffuse layer. If the reaction is happening in the bulk solution, then you may not get any signature based on your biosensing. So it's very important that the reaction is chosen accordingly. Now, these particular layers forms two different types of capacitance. So if you look at the charge here in the Stern layer, you'll find Stern layer capacitance, and then in the diffuse layer, you'll find diffuse layer capacitance, which is also known as Gauss-Chapman layer or Gauss-Chapman capacitance. So entire gate capacitance consists of this Stern and diffuse layer capacitance. Both are in series. Now, in case of pH sensing, depending on the pH of that particular solution, either H plus or OH minus will dominate, and based on that, these capacitance will change, and that will help you to detect the pH of that particular solution, which is present in this electrode. Now, this is the fabrication part. So we have used CVD grown graphene, and we transferred that graphene on a polyimide substrate using thermomechanical process. So there is an optimization associated with this. So either people transfer it with thermal process or mechanical process, but we have optimized the transfer method using both thermal and mechanical. So we call it thermomechanical process. And then we could transfer 5 mm by 5 mm graphene layer on top of polyimide. And after that, we developed two different FET structure. The first one we call GR-FET1, Graphene FET1, and the second one is Graphene FET2. The Graphene FET1 has an interdigited electrode in terms of source and drain. However, the Graphene FET2 has a conventional geometry where you have a source, drain, and then you have a gate. The first FET we used for environment monitoring, the second one for health monitoring. However, you can use the first FET for healthcare monitoring as well. But in this case, the leakage current is little higher. So we found that for pH sensing, this FET is more suitable. So we use this for pH sensing and this one for biosensing. So this is the fabrication process. So you have a transferred graphene on an polyimide substrate. You printed the source and drain, and then you have created a well for the electrolyte, and then you have a gate electrode present, which we treated with chloride to form AgAgCl, so that we can reduce the gate current, and ultimately you get a device like this. Similarly, for GRFET2, same process we followed. And then we passivated the electrode, in this case with PDMS insulation, which helped us to get even lesser leakage current. And then you have a device like this. These are some of the results. So without chloride treatment or with 10 minutes chloride treatment, you see that the output characteristics is not that good. The transfer characteristics is not that good. But after say 25 minutes of chloride treatment, we could get unstable transfer characteristics, which is kind of U-shaped. We also characterized the material with FESM and EDS. And this is how it looks when AgAgCl forms. We did this study for different chloride formation at different stages. So we figured out anything beyond 25-minute chloride treatment, we got a very good BCNB, meaning a very good transfer characteristics. And this is how the device looks like. This is again the FESM image of the gate electrode, where we could see the formation of AgCl with time. So we treated this particular gate electrode for 15 minutes, 5 minutes, 25 minutes, and then we could see after 25 minutes, it more or less have formed AgAgCl. We studied the gate current characterization with AgAgCl at different stages of formation, and we could see after 25 minutes of treatment, the gate current reduces to 2.75 microampere, which was initially more than 200 microampere. So that reduction in gate current actually helped us to get this transfer characteristics that you see, that U-shaped transfer characteristics. So this is again the output and transfer characteristics of the GRFET1 with different drain voltage. We have characterized the device, and we could see an increase in current, which should be the case in case of FET structure. We further also analyzed the hysteresis of the transfer characteristics for both backward and forward voltage condition. What we could see is for an high voltage rate, if you change the voltage in the gate at a higher rate, you see a higher amount of hysteresis, which is basically because of the charge transport or the time it takes from time it takes to reach to the say source electrode from drain or drain to source. And because of that, this hysteresis is high when the voltage change rate is very high. So one solution could be, if you reduce it to 10 millivolt per second or lesser, you see that the hysteresis is much lesser. It also happens, another reason could be the local electric potential due to the capacitive gating. But in both the cases, low voltage rate helps. So you get a very less hysteresis in that case. This is the comparative study of our graphene FET with the reported one. So we could achieve very less leakage current. And then the transconductance values are also comparable, if not lesser. So we could actually got a very good result in terms of printed graphene FETs. We compare with previous prior arts. So this is the pH sensor calibration with different pH. You can see that the VCNP is shifting, and then we could get a fairly linear characteristics for the pH calibration, which we can use for pH sensing of a particular solution. We also functionalized graphene with antiferritin, and we detected ferritin in blood serum. Again, we got a fairly linear I won't say it's completely linear, but in two different ranges, we got two different linear characteristics for ferritin concentration. So the ferritin biomolecule is one of the biomarkers for sickle cell anemia. So we are trying to detect sickle cell anemia at a very early stage. So in summary, we developed two different types of FETs, one with interdigited electrode, another with conventional FET structure. And in both the cases, we could achieve a good result in terms of sensing. Now I will briefly discuss what else we do in our lab. So I will not go deep into the topics as we move forward. For example, we also do science. Being at IISER, it's very I would say the science is quite accessible even in other institutes also, I'm sure. But we also collaborate with other departments, other natural science departments. So we started an project with single crystal small molecules, which is known as 4CFNCS. And this particular single crystal molecule has an inherent bending property. So we tried to harness this bending property for a pressure sensing application, and we could get a very good result in terms of pressure sensing, although it's not the best result that we could get. But we are still doing more further research in order to improve the result of the pressure sensor. Apart from that, I also work with chipless sensing antennas. So recently we could develop an antenna that detects different degree of bending. So the idea is whether we can use the antenna as a sensor, which may help to reduce the size of a particular device. So this is mostly for smart packaging application. And this particular sensing antenna works at 3.9 gigahertz. We are trying to reduce the working frequency so that we can bring it down to say 2.4 or little up and go to 5 gigahertz domain. We also develop smart sensing for thermal perception. So we are developing sensors, integrating these with different gloves to make it smarter so that the gloves or and robotic system can touch something and can get a thermal perception of a particular object. In that line, we are also working in the area of smart sensing for surface perception. So the idea is if we attach different pressure sensor, basically these are multimodal sensors. So it's a pressure plus temperature sensor attached to different robotic and gloves. And if you touch an object, this can identify whether it's a cemented surface or soil surface, or it's a mud, or it's a glass surface, so on and so forth. So we applied machine learning algorithm on the data that we have received from different surfaces. And we could get, at this stage, we could get around 87% accuracy. We are working on this particular sensor so that we can improve the accuracy further. So these are mostly for smart robotic applications. And then recently, we also have developed an image sensing technique for TB analysis. This is in the healthcare domain. So this is in collaboration with AIIMS Bhopal. So they have identified 5 different unique biomarkers. And these biomarkers show some colorimetric changes on their device. They have developed a device which is known as RDT, Rapid Diagnostic Test Device. But the problem is when they deployed it in a rural setup, many cases whom particular RDT are unable to figure out whether there is a positive case or negative case, or if it's a chronic case or early stage case, because most of these are decisions are taken by the color differences that they may get in this particular device with a naked eye. So we developed a mobile application and implemented machine learning algorithm in order to identify even one shade change in any of these spots. So we could achieve more than 97% of accuracy. And this also has been published. These are some of the products. So we are also developing smart modules for respiratory illness. So we are trying to make a normal mask a smarter one. So these are some of the modules that we have developed. We are working on it. We also developed some of the health bands for cardiac parameter monitoring. These are some of the low noise amplifiers for sensors. for wireless transfer. So these are also recent developments that we have done in the lab. These are some of the sensors that we developed for impact sensing for smart packaging applications. This is another smart module to make a mask smarter for respiratory illness and so on and so forth. Some of these we are also planning to commercialize. For example, this GRFETs we are planning to commercialize maybe very soon. This will be available in the market, and then people can buy and functionalize those GRFETs to detect various biomolecules. Some of the works also have been covered in the media. So these are the areas, and more or less I have completed my discussion. I would like to thank the group members, funding agencies, IISER Bhopal, and my collaborators. So if you have any queries,